Thanks, Rosé. Yeah, slightly misleading picture of me here. It was a few years ago when I joined Graphcore. I did some work in product support, then in MLOps, and now as an ML engineer. So I've been working on some training, on some model training lately, and with a release from DeepSeek, I got the opportunity to dig into the papers, how they did stuff, and thought it was a good topic to talk about. And that was DeepSeek from First Principles was the title I thought of 2 weeks, 3 weeks, a month ago. Really, we were going to try and answer how did DeepSeek suddenly make training a front-end model 10 times cheaper. So we're going to have this is a brief outline, a bit of context. Why would we care? Then what is a transformer anyway? Because it's a word that's thrown around a lot, but I'm sure there's some details in there that really impact how you deploy it and the computational costs. And if you don't understand those, it can get a bit tricky. And then how did DeepSeek really change what the expectation of the cost of a training run was? And then maybe, did they actually change what it was? So I want to start with a bit of a timeline of relevant research. All the details are not all important, but we start in 2020 where we have some papers from Google called G-Shard. And then in 22 we have other things called switch transformers and faster MOE. And here we have some background into some of the first papers which start looking at how we can make transformers significantly more efficient. Then if we look in 2023, we have two really big releases in what are called mixture of expert models, and I'm starting to spoil a little bit the end result, which is that those mixture of expert models are one of the keys to reducing the cost of training, and the rumors are that GPT-4, which was released in March 23, is a 1.8 trillion parameter mixture of expert, but in the open source world, in December, Mistral released their Mistral model. And then if we look through 2024, there's a lot of releases. It was tough to keep up. But in February, you'll notice that DeepSeek was already releasing models. And I became aware of them then because I was looking for the best model for coding and the best open source model for coding. And they had one of the best. So these guys are a really talented team, but that have been releasing consistently through 2024. And a bit before, with some really important contributions to the open source community, which some of the maybe more the open AIs are not sharing. So, and then finally in 2025, in January, they released DeepSeek R1, and then they broke the internet. So I'm going to cross out the first word. How did they suddenly make training a front-end model 10 times cheaper? Well, it took them at least a year, and they kind of spread out their releases. So it wasn't quite as sudden as, they didn't come quite as out of nowhere as you might think. Then let's define the other terms, cheaper and frontier. So these guys are probably the ones that we'd recognize as the frontier model providers. We've got OpenAI, Claude, and Anthropic on the bottom, and Gemini. Unfortunately, they don't say anything. So I can't really talk about what they do. I don't know how much it costs them to do anything. They can argue about it in blog posts, but really I don't have anything to say about it. So really we're going to be looking at the guys who write about what they do. So we've got Meta, DeepSeek, the little whale, but then a bit of Mistral. Does anyone know what this one is? Have you ever seen it? That's the Allen AI research group in Seattle. They publish some really good models, and they have the sort of most open pipeline in the market. So it's really interesting. They publish some really interesting stuff to pay attention to. They'll publish the entire data sets for reproducing their research. So what is the state of the art? We're going to define it as competitive with closed source LLMs on most benchmarks. There's hundreds of benchmarks. Everyone cooks up their own to make themselves look better. But we'll take a broad range. We'll look at models which have sufficient information on how they were trained so that we can get an idea of what they cost. And then we'll limit it to open weight models, because if you can say whatever you want. If you're not releasing the model, you're not sharing much. So the one we're going to use as a benchmark is this rather dopey looking llama with, in particular, the llama 3.1 with 405 billion parameters. It's not a model you really want to be running. It's expensive, but it's possibly the one where there's one of the most detailed technical reports as to what sort of infrastructure, the efficiency they achieved during when using it. The software behind it is fairly open because they use mostly PyTorch. And then they derived a lot of things like scaling laws and how to build in multimodality, which really gives you a quite complete picture of what it took to train that model. So why should you care? Well, apparently you just do. That's the interest. So the second bit is that there was I don't know if you heard, but I read afterwards that there was a bit of a stock market movement. And then the last bit, this is Andrej Karpathy, for people familiar with ML engineering. You've probably heard of him, but he recognizes the DeepSeek publication as a fairly important contribution. And he's one of the great teachers of ML in the world. So if you don't know about him, go and Google his name. Well, you'll find his YouTube videos, very incredible resources. On a more practical level, why would you care? Maybe as MLOps engineers who are you're trying to deploy some models, and you might be using APIs, and you're confused. Why are token prices different? And like digging into the architecture and how it's deployed, and a bit of how it's trained, understanding those basics can help you understand those differences. So, for example, here this is the language, the LM Arena from LMSys. They have now a price comparison. And so what I want to highlight is that DeepSeek, when they serve their model, are very cheap. But when other people serve it, they serve it for 3 times or 4 times the price and change a bit the balance of performance. And so on the y-axis, you have got the performance of a model in the model arena, which is just a way of rating models against each other rather than against fixed benchmarks. And you've got the cost per token. So there's something a bit weird going here that depending on who's providing you the API, it costs a different amount. Now we're talking about DeepSeek and Llama. What lies behind those names? So Llama is a decoder-only transformer. We'll cover what that is. It's 405 billion parameters. So if you try to fit it in NVIDIA GPUs, the top of the line has more than 80 gig now. But out of 80 gigs, you need 6 of them to fit all the parameters, in FP8, so in quite a small format. It was trained on 15 trillion tokens. It used 16,000 of those H100 GPUs to train, and it used 31 million GPU hours. Giant numbers, giant numbers, giant numbers. DeepSeek v3, decoder-only mixture of expert, our first difference. 627 billion parameters, that's actually a lot bigger. And then similar number of training tokens, a much smaller cluster, and used a smaller number of GPU hours, still obnoxiously big, but move on. So what is a transformer? So this is a transformer. You've got some maths. How did DeepSeek make it faster? You implement it in CUDA and assembly. You make it an MOE. You train it in FP8. You invent dual pipe. You balance the expert parallel stuff, and you're done. Here you go. Thanks. Okay, I'll try to avoid some jargon, but we're going to go into a bit more detail. We have a flop, so I want to give some background. So a flop is a floating point operation. It's just one matrix multiplication or one addition. Flops, it's either the plural of flop or flops per second. Sorry. A mapmul is a matrix multiplication. Like that, I've spelt it out once. What's a billion? If I have a little b, it's a billion. If I have a little t, it's a trillion. And then you might see some BF16, FP16, FP8, FP32 in the slides, they're floating point formats, so numerical representations of decimal numbers with different number of bits. So 16 is 2 bytes, 2 times 8. FP16 is also 16, slightly different representation. FP8 is 8. 32 is 4 of those. So what is a transformer anyway? It takes some text, we put it through a tokenizer to get some vocab, to get it from the string representation into an integer representation, so a numerical form. Then we pipe it through this paper, which is attention is all you need. Probably just need to read it. And then you go through, you get your new sequence of tokens, which you pass through the tokenizer again, and you get a string that you can read it. So now let's visualize it. So we have the structure of a transformer, which can have an encoder on the left and a decoder on the right. That's the sort of traditional architecture. For generative workloads like Llama and DeepSeek, you're using a decoder-only architecture, so just the right part. And then inside the encoder and decoder, we have 3 main parts. We have the embeddings, the transformer blocks, which is the meat of the model, and then the output head. And all the diagrams I'm getting are from this lovely website, which has lovely interactive representation of a transformer, and you can go and see what number multiplies with which number to get to the result. It's a nice way to understand it. So what is an embedding anyway? We're not going to cover that in too much detail, but essentially you're going from a single integer token to a really big vector for each of those tokens, which is the hidden representation or latent space of your model. And the key implementation concern you're going to have is that the size in memory is very big, and the pattern of computation is really different from the rest of your model. And that's a pain, but you deal with it and you move on. So the most important bit is the transformer block. So we have, again, 3 parts. We have multi-head attention, which we'll cover in more details. We have a projection to go from this attention to the multi-layer perceptron, where most of the weights of your model are stored. And there will be many of those transformer blocks inside a model, maybe tens to low hundreds. And why do we use this pattern? It's because it's really good. It's got a regular structure of computation, which is good for applying optimization. So all the layers are the same size. We can distribute those, pipeline them over several accelerators. It makes it really predictable. It makes it easier to parallelize. So one of the challenges of multi-head attention is that you have many small matrix operations. So you're taking your embedding vectors, you're putting them through QK and V matrices, which are these weights, those 3 matrices are learned, and we calculate a score which represents the impact of previous tokens on each one that comes later in the sequence. So through the softmax, we get this relationship between tokens. So now, why is it called multi-head? It's because we have tens to hundreds of heads which have the same pattern for each layer of attention. The key difficulty with this is the sort of memory bandwidth for accessing those intermediate results. So what's difficult with this is saturating the mapmul hardware for each flop, so for peak flops. So you have all these small matrix multiplications. You really want to feed that to the things that is going to do the operations as fast as possible. The rest of the transformer is pretty straightforward in comparison. It's a lot of big mapmuls. You've got the projection to go from the embedding shape from the attention to the embedding shape, and then the multi-layer perceptron, which are 2 fully connected layers and a nonlinearity. The big concern is fitting it in memory and just the sheer amount of flops that we need to do this. And finally, let's not forget it, we have an output head. So this maps the logits, so the output of your last layer, into a probability distribution. So this will be task specific. So for example, if you're doing token by token generation, you're going to try and predict the next token. If you're doing classification, maybe you want to train another head to to give you some specific labels without doing token by token generation. And for autoregressive generation, we're gonna sample that distribution, and this is where your temperature and your top K and your top P come in. So those are where those parameters come in and tweak. And for example, beam search will happen inside the head. So I've shown a very small model, but if we are looking at how big real models are, the embedding size is 16K, 128 heads of size 128, which I think amounts to 16K again, which is quite convenient. And then the hidden size is roughly 4 times, or exactly 4 times the embedding size. And we have 126 layers. So, yeah. How do you make it cost less to train? Because that was a lot. So what drives the cost of training? We've got the cost of AI hardware. So for an H100 is $2 per GPU. For other hardware, it'll be slightly different. But that reflects the energy consumption in general and the outlay you need to buy it. And then the goal is to use as much of the flop capacity of the hardware as possible. So you have 3 options. You make them do less map moles. So can you shrink the model? Can you find algorithms that reduce the number of map moles you need to do? Can we make the map moles cost less? And can we spend as much time as possible doing those matrix multiplications? So we're going to go. We said this was from first principles, so we're going to go and calculate the number of flops that a map model takes to try and understand how many flops it takes to train a model. So we have we have 2 matrices, which we are going to multiply, so you'll notice that the sizes have to match. The refresher for a map model is that the map model is a dot product of the rows of A with the columns of B. So to calculate one element of the output matrix, I'm going to do P multiplications, so in our case 7 multiplications, the inner dimension, times twice, well, I'm going to do 7 multiplications and 7 additions to reduce it into that element. So in general, we have 2 M by N by P flops per matrix. So now how does this apply to a transformer? You can assume that all the calculations are matrix multiplications. It's a simplification we can do for a transformer. It's not quite true, but it gives you a 95% estimate. So well, I think 99% estimate. So we'll skip attention for now. So in the forward pass, we have the hidden representation of one token. And this hidden, if we think back to our representation of a transformer, that token is being passed through all these matrix multiplications in the QKV matrices, in the MLP. And essentially that hidden dimension is going to be processed through each parameter of the model. So we can say that for a transformer, the flops required are exactly 2 times the number of parameters times the number of tokens. So that's the number of tokens we see in a training run. So that's the 15 trillion tokens that are mentioned. Whether those are the same every time or not doesn't really matter, or whether there's any repetition. That's the number of tokens we're going to see. So we can make this approximation that for the forward pass, we require 1 matrix multiplication. Now we need to consider the backward pass. I have 2 gradients to calculate in my backward pass. I have the gradients with respect to I'm the gradient of the parameters with respect to the loss. I could have written this a bit more clearly. And that also, when you do the maths, it turns out that it's you have the transposers of the inputs times the grad of the loss of the previous activations, and that comes out at a matrix multiplication which has the same size as our ultimately this is many parameters. So we have 2 MNP again. And the second gradient we need to calculate is the gradient of the loss with respect to the inputs in our layer. So we have 2 extra matrix multiplications on each step. And so this is one of the canonical results that you might see quoted quite a lot, is that the total flops for training a transformer is 6 times the number of parameters per tokens. And that's where it comes from. 1 matrix multiplication in the forward, 2 matrix multiplications in the backward. So now, can we do less flops? Well, when we have a dense feed-forward network, the matrix actually looks a lot like this. This is your weight matrix. It gets much bigger. And what we find is that we have a lot of numbers, actually, once we fed them through the transformer, which are very small, so have very little impact on your next layer. And the idea is, can we do anything to not compute those values? And that's where mixture of experts come to the rescue. So you take, instead of this one big matrix, you replace it with a few smaller ones. So, and you'll notice here this matrix, oh, I didn't mean to do that, but this matrix is exactly 1/4 of the size of the big matrix, but there's actually 6 of them, which represents sort of a ratio from Llama 405B to DeepSeek v3 in terms of total parameters. DeepSeek has more parameters, but the trick you're going to use is you're only going to use the 2 most important of these matrices to calculate the next step of the next layer of your model. So for each token, you're only going to pick a few of the experts. So this is usually a small neural network, and you're going to pick the top values which correspond to these matrices. And those are the ones you're going to process your token through. Now, if we revisit our flops for a mixture of expert, and this is where we have our total flops for training a dense transformer, which was 6 times the number of parameters per token. But for a mixture of expert, the number of flops are 6 times the number of routed parameters per token. So the routed parameters, they correspond to the QKV projection parameters, which are always there. And then the sort of number of active experts versus the number of total experts times the size of an expert. So these experts are just these matrices which are either turned on or turned off. Now, when we look at DeepSeek v3, what we see is that the number of active parameters for each token is actually 37 billion. It's a number that will get quoted quite a lot. And it's these parameters which are turned on for each for a token. And so what that amounts to is an 11 times reduction in compute, or it's 11 times more compute to train Llama 3 than it is to train DeepSeek. So we're starting to see where our 10x improvement in cost might be. So what is this? So what is different about this Mo? Because there were mixture of expert models before. So I mentioned Mixtral, DBRX, maybe GPT-4. The point is that before we have this sparsity ratio, which is this ratio of active over, the ratio of total over active parameters. And they lie in the range of 4 to 10. So this is, you get a reduction of 4 to 10. In terms of the training compute compared to a dense model of the same size. With DeepSeek v3, we're looking at 18 times. And this is maybe one of the engineering achievements that they have, is that they have managed to train an MOE with that sparsity rating. It wasn't clear that that was really feasible, and they're definitely the first ones to write about doing it. So why doesn't everyone use a Mo? There's significant engineering challenges that come with it. The first one is load balancing. So we talked about this really regular structure of computing that comes with a transformer. That's broken down when you have different experts which get dynamically routed to a different amount of tokens. Suddenly a different expert is doing a different amount of calculation. So it becomes much harder to distribute this over multiple GPUs. Training stability is an issue because of that routing. Whether it's because of that routing or not is not clear, but there you can see loss spikes. So the Allen AI research group I was talking about earlier trained a mixture of experts, and they reported that they really struggled to get it to stabilize in training. In terms of parallelization, I briefly touched on it, but the idea of expert parallelism is split your model with different experts on different pieces of hardware. That's difficult to do, again, because you have this routing problem. So if one accelerator receives more tokens, it'll take longer to process, and all the others have to wait, and then you lose efficiency. And then the final reason is that you have an increase in model size. So, and all of those experts need to be loaded into memory that is close to your accelerator. So it'll be HBM on a GPU. So DeepSeek v3 is 65% bigger than Llama 3. The fact that there's 37 billion active parameters does not save you at this point. You still need to load it into your accelerator. So now let's think about, we've reduced the number of flops, but can we make each operation cheaper? It turns out, yes, we can use lower precision formats. So traditionally, if you come from HPC, you'll have used doubles, so float 64. Commonly, you'll use float 32, so one sign, this is the sine, exponent, and mantissa, and those will have a lot of range and quite a lot of precision. In ML in the last few years, or for maybe 5 years now, people have been pushing to use mostly float 16, well, bfloat 16. The benefit of bfloat 16 is it has a high range, so it has the same, it represents the same range of values as float 32, because the exponent is the same size. They both have 8 bits. And the next barrier is going down to float 8. The challenge there is you have a much smaller range, so the biggest number that you can represent is much smaller. And also within that range, you have much fewer steps you can represent. So when you sum all those numbers together, you get a lot of numerical instability issues. But the last pro is that if implemented in hardware, these operations can take less energy, and each number is much smaller. So that means that your tensor with billions of parameters takes less memory, but also less communication between your accelerators. So in a setting where you're running vectorized operations, you can do more of them at the same time. The challenge with those is the numerical stability when summing a lot of those numbers, and that leads to complex quantization schemes. So this is, on the right, is the scheme that it's a microscaling scheme that DeepSeek came up with, were implemented, which lets them do a lot of their matrix multiplications in floating point 8. And they've done that despite the fact that the hardware they have access to does not support it. So it's really some fiddling with assembly to get it to do it on the right core and add some scales up. But the really interesting point is that what was not clear at this stage, there's suspicion that maybe Anthropic and OpenAI had been using FP8, but it was unclear as to whether they were successful with it. With DeepSeek, we have a confirmation that it is possible to train a very large frontier model in FP8 at scale. Okay, this has been a lot of theoretical flops, that hand paper calculations, but at the end of the day, that's not your cost. And there's this concept of model flop utilization, so the ability of your model to use the flops provided by your hardware. And so your hardware has a rated flops number, so maximum it can reach. So how much of it can you achieve in practice as you train your model? The challenge is that models do not fit in memory, so it's not just that I just load my model and I let it run as hard as possible, is that I'm going to need to distribute this model over many optimizers, many accelerators to get it. So for a 671 billion parameter model, we're talking if it was in BF16, that's 1.3 terabytes of RAM that you need. So just to hold the weights. But you don't just hold the weights, you hold the gradients, you hold the optimizer state, and some activations to calculate your backward pass. So if not accounting for activations, I need 67 accelerators working together just to load my model weights. So this becomes a very challenging parallel programming problem very quickly. So what did I say about this? So how do you minimize your communication to ensure you use all the available compute? So to understand how efficient they needed to be, we can think about those, the headline number from the paper is 2.8 million H800 hours. They have the same number of flops. So, and we can remember our calculation from earlier. We need 3.4 times e to the 24. That's a crazy number. It's trillions of trillions flops. So we can calculate the number of calculations, so flops, which are available for this number of hours using the hardware they had access to. So in BF16, that would be 989 teraflops, which spread over 270 million hours. You've got 1 e to the 25. At least our napkin maths work, because that number is bigger than the number they actually did, which is good news. And in FP8, we're looking at 2 e to the 25 flops. So this is the fact that the NVIDIA hardware there can do FP8 maths at twice the speed of BF16. So from these numbers, we can calculate a required efficiency. So how efficient did they need to be to train the model in the time-based state? And about 34% in BF16 and 17% in FP8. The Llama report states their efficiency via their MFU, and it was in the 38 to 45%. That doesn't sound great. Like, I don't know, 0.3. If you got 30% on your university exam, you wouldn't be very happy. But the reality is that from these headline numbers to the reality of implementing it, well, you lose 25% in the power limits of your GPU. That 989 is based on independent benchmarks, almost inachievable. Then in terms of transformers, they're not just matmults. You lose another 20 and 30 to 30% between attention and the normalizations. There's some layer norms inside your model, and vectorized operations, which take some time. And then finally, you've already lost about 45 to 55%, and you need to squeeze in synchronization between 2,000 GPUs. So it's quite an impressive achievement to still reach those 35%. So we've covered the MOE pattern. So how did DeepSeek make it work? Specifically, they had a few more innovations which really came in, which gave them a few extra percent of either in flops or in benchmark improvements. So in their DeepSeek v3 paper, they talk about multi-token prediction. That's they change the head and train it to predict a second token. And the benefit of that is they found it trained a smarter model, so they gained 2% on benchmarks in terms of MMLU and whatever. But also in inference, you can use that to predict a second token and use it for speculative decoding. So if you've heard of speculative decoding, is you have a model which is dumber than your big model, and you get it to predict a second token. You get it to predict next tokens, and in the meantime, your main model is either generating or checking the next token. And that means that with that second pass, with that speculative decoding approach, they get 85% acceptance rate, which amounts to a 1.8 throughput improvement. Finally, no, not quite finally actually, we have the loss-free load balancing of experts. What they found is they have this method which lets them choose the best experts and makes their 64-way expert parallelism really efficient. But other methods that do this tend to impact the representation of a model and mess with the output. And what that means is that they manage to get a 1.5%. They do some analysis where they remove this improvement, and they find that it's 1.5% improvement in benchmarks on some smaller models. So that's the challenge with doing such a big training run, is you don't know what happens at that scale until you try it. You're only doing one, or you're probably only doing one run at that scale. So you need to do smaller experiments on smaller models. Smaller, still 200 billion parameters on 1 trillion tokens. Finally, that was much touted, was their dual pipe algorithm. It's pretty clever, but it gives you great computation and communication overlap in pipeline parallelism. It's unclear whether some people made it out to be the sort of breakthrough that made it possible. It's probably not the breakthrough that made it possible. It's one of the sort of incremental good developments, but without necessarily being, and it might be more applicable to their cluster than it is to everyone else. So it's unclear whether that one is benefit is it doesn't impact your model. So what drives their lower training cost than previous frontier models? First is that very high sparsity ratio of 18 in the mixture of expert. It's kind of a boring outcome because it's like, okay, well, they made it work. But the reality is it took some truly excellent engineering to make it stable and efficient and work well on their cluster. However, when we look at what that headline figure, we need to add a little grain of salt, because what's missing from this calculation are all the experiments, the previous models that they used to train. So you're looking at, they have it's a V3. You'll be surprised to learn there is a V2. There's also V2.5, because that's trendy to have half measures. And they all came in the year before, so I could have tried to do the napkin math, but that would have been very deep supposition. But there are a lot of experiments that come before you do this big run, and those are not accounted for in this headline figure. Their other big development is DeepSeek R1. And there, I think it's probably their biggest scientific contribution over the last few months. And it's the fact that they've shown that this group relative policy optimization, which is this reinforcement learning approach, which they published in their DeepSeek math paper in, I think it's April or May last year, where they showed that like on those narrow themes where there's a right answer, it works really well to improve that reasoning performance. They've shown that this method seems to work really well to teach a model to reason out of, without any other. If you're familiar with reinforcement learning, you usually have what's called the policy model, which is the model you're trying to improve, and you have the reward model, which is telling you, like how well you're doing. And those are similar sizes, so it makes it really expensive. You have multiple models to handle. If you're a reinforcement learning expert, I'm sorry, because that is just probably not a great explanation. And with R10, they used pure GRPO, so no safety supervised fine tuning. And with R1, they used some the traditional fine tuning to make it instruction following. So like they do in Llama, so that it respects your chat templates. And does what you ask, not random generation from its pre-training corpus. This is the image I expected to see appear earlier. But this is a representation of GRPO, and the idea is you get your model, you give it a prompt, and you get it to generate a bunch of responses, and you're going to say, actually, I'm going to let it spout a lot of reasoning, and then I'm going to say, actually, I want your answer. Your answer is going to be rated with respect to the average answer, with respect to the mean. So there's something quite weird going on here, that by making the model tend towards the average distribution, when you have a strong starting model, like DeepSeek v3 or some other frontier model, pre-trained model, that you can sort of make this reasoning pattern in this long context chain of thought emerge. So, final slide. How do you efficiently deploy DeepSeek according to DeepSeek? Do we have any guesses? In inference. Someone risk it. How many GPUs do you need?
I was going to say, just use their API.
Yeah. It's good, clever.
5 Mac Mini stack.
Sorry?
5 Mac Mini stack.
Yeah, okay.
Bunch of PlayStation 3s. No GPUs, just CPUs.
Yeah. So their recommendation is that you need 32 GPUs for prefill and 320 GPUs for autoregressive inference. Yeah.
What GPU?
They are using H800 NVIDIA 80 gigs of memory. So that's their recommended setup for efficient inference. So what about Llama? They tell you, okay, you can probably get by in their paper with 2 by 8 H100. And what's interesting for me here is that those two models probably represent some different part of the sort of the optimal design. So while Llama is maybe more expensive to train, it's easier to do fine-grained scaling in inference. So I can just boot up. I just need 2 instances of very expensive hardware, but I don't need, my unit of deployment is not 352, which is impossible to handle. And so if we look, I could look back at the first slide, I should have put it here, but DeepSeek's API has peak hours and low hours. So if you're going in off-peak hours, they cost 1/10 the cost of when they are in peak hours. And that's probably because of this, because they can't scale it down to something really sensible, and they have to keep paying for this huge amount of hardware, so it becomes cheaper for you. Llama as a dense model is also a bit easier to scale in model size, and it'll be easier to fine-tune and add LoRa adapters, because if you're doing LoRa adapters on a mixture of expert model, you're going to face the same loss spikes and engineering challenges that a DeepSeek have faced. So a few conclusions. DeepSeek has been delivering excellent research throughout 2024, so it didn't come out of nowhere. V3 is a really impressive engineering achievement. I've spent a lot of time reading that paper and thinking about how they did it, and some of the numerical things that are going to be talked about by Alex afterwards are exactly the sort of things that as hardware manufacturers we're thinking about, and is our main job to predict the tea leaves. So in their paper, they actually had some recommendations for hardware vendors. So it was good for us to sanity check that actually we were doing those things. I can't say whether we are or not, but This is what it is. DeepSeek R1 is really a genuine scientific achievement. If OpenAI wanted to claim it, they should have published. And then one of the challenges, though, with DeepSeek's work is that their work is hard to reproduce, as it relies on a lot of compounding engineering, and they've been releasing quite a lot of those materials, but they're not always really easy to run. It's not as out of the box as the sort of Llama outputs. And then the headline $5.5 million omits all is correct for the final training run, but omits all experimentation. So it's up to you whether you take it at face value or you go and argue with people as to whether it's true or not. My final opinion, it's not financial advice. You're still going to need hardware to run LLMs and reasoning models. Those reasoning models really like to generate a lot of tokens. Got mentioned, we're hiring. Please flash this QR code. I get a referral for everyone that flashes this one, and Alex gets a referral for everyone who flashes the other one. And thanks for listening. Any questions?
Anyone has any questions? Let's spend 5 minutes in questions. Anyone else?
I have a soft throwable microphone. I won't throw it at everybody else.
Thank you very much. When they're saying they need 320 cards for optimum inference,
Yep.
is that for some given enormous concurrency? Because like technically you could run that on like I've seen people on the internet thing on like one Mac. So what's the 320 cards for?
So when you see it on one Mac, I'd watch out as to whether they're running the full fat model or not.
Yeah, 671p on like a serious Mac.
Okay, impressive. Must be slow. The reason they do it that way is it gives them, it's using a lot of parallelism, for which they can overlap all the communication and hide a lot of the latency, which lets them achieve a really good user experience in a sense, because you have really high prefill. So the sort of your sequence is processed first really quickly, and then you can have a really high next token, like a really small time per output token. So it's really optimized for that. The idea is you run one expert per GPU. They have 257 experts. They have some for redundancy, but it's a really optimized setup. And this is also why the others are probably charging I was showing Fireworks AI's pricing for V3 and R1 are slightly higher. It's probably because they're not using that 320 setup, so their token economics don't make quite as much, are not quite as optimized.
Thank
I think we've got time for one more now to move on. I've got a terrible here.
You did great.
As far as I understand it, I'm probably too crude around understanding here. In your multiplying of expert layers and your attention part of it, you're basically throwing away 2/3 of the data, and it tends towards the same result anyway. Can you throw away that 2/3 somewhere else, like randomly at the input, or reduce the size of the matissa in your number format so you're ending up only with 1/3 of the accuracy? Would that be a simpler way of doing it?
So in terms of the floating point representations of the...
Yes, so you're equivalently reducing by 2/3 the amount of data, and it'll be simpler? Or is that just too simplistic?
So I think the challenge with there is that we start getting into how you actually design hardware and to implement the sort of we can come up with things that would work in software, but that would not be implementable in hardware in terms of bit shifting and doing that sort of stuff.
So a multiplier at a lower level of accuracy will take the same amount of time as a high level of accuracy because of the way the GPU is designed internally, so I'm barking up the wrong tree or something.
I'm not quite sure I followed the entirety of the question. So.
Well, because you're throwing away 2/3 of the data internally, can't you throw away 2/3 of the data at the beginning and then
We're not.
use the normal model?
We're not throwing away 2/3 of the data. We go to a smaller floating point representation, but we're hoping that our data is still adequately represented by it.
Right, so you're reducing the accuracy of the calculation by 2/3 then instead, or?
It's well, yeah. Alex is going to talk more about floating points, so you can probably direct it to him. But what you hope is that you are doing this reduction and reducing the amount of processing that you need to do, but that you are not losing that you're not in that accuracy range where it's very critical, and that it's still representative enough of the operations. So if you start having 1 + 1 = 1, then you start having a really big problem. And that can happen, but you are trying to stay in the range where 1 + 1 is equal to 1.999. I'm not sure it's a very good explanation, but I think we need to move on.
Thank you very much, Alex. Right, so we've got another lightning talk. So it'll be 10-15 minutes where Alex from Graphcore is going to deep into a little bit more detail into some of these optimizations. And then we can have a break, have some pizza, which I believe they invite already, and have another drink, and then come back for the second mic. Okay?
Thank you.
Right. Thank you very much, Alex. And yeah, take it away. You have both mics.
There's two.
Sorry, double mic.
Yeah, there we go. Let's put these on. There we go. All right.
That's one, and that's the other one. There you go.
Cheers.
Thank you.